So at this point, your problem set should be up to 130. We'll start with questions. Does anybody have any questions on any of that stuff? I think we've assigned up to 130, so if there's questions on anything, happy to, knock those out here before we get started with the regular stuff. Anybody looking for one, or we more or less either we think we're good or we just don't know because we haven't gotten very far in. We just don't have anything to say. That's fine. Yeah, that's fine. Fair enough. I just want to know whether should I be waiting or are we good to go?
I got the 78, but
yeah, fair enough. I get it. All right. Well, let's just get going with the stuff then. So we're just going to kind of continue with 15.4. We'll finish that up today. So we started 15.4 and we talked about solving exponential and logarithmic equations. And basically we just developed the algebraic tools to do that for these contextless equations, right? The second half of 15.4, we're going to look at some actual applications, some actual situations that involve or that can be we can be modeled using an exponential or logarithmic equation, and we'll do some solving in those specific contexts. Okay, so it's basically story problem kind of time, right? So there's a couple of or several real life scenarios that involve both exponential or logarithmic equations. So the first one is sound intensity. So our equation for sound intensity is this. Does anybody know offhand what sound intensity is measured in? The unit?
Hertz.
Not hertz. Decibels, yeah, very good. So the beta here is just number of decibels. And the abbreviation for decibels is dB, where the D is lowercase, because the prefix deci, the symbol is the lowercase d. I is our sound intensity, and the unit for sound intensities are in watts per meter squared. And then I naught is a constant. It's always 10 to the negative 12 watts per meter squared. So let's look at an example. Where did that go? There you are. Given that the sound intensity of busy city traffic is approximately 10 to the negative fifth watts per meter squared, what is the measure of busy city traffic in decibels? Hopefully, from the wording in this, there's no doubt in your mind that this is modeled using that sound intensity model we just gave previously. The question is asking for the measure of in decibels. So what are we going to be solving for? Which symbol in the equation? The beta, yeah. Okay, and so we have to fill in this 10 to the negative fifth. What symbol is that going to go in place for?
I.
Good, that was the sound intensity, so that should be the I. And the I naught is, again, the constant. So we're just kind of plugging stuff in. And that at this point would be calculator time, but you don't really need a calculator here. 10 to the negative fifth divided by 10 to the negative 12th is 10 to the positive 7th. Log of 10 to the 7th is 7, and 7 times 10 is 70. So we have 70 decibels. You guys ever watch the football games where it's like in the fourth quarter and they show the sound meter on the TV screen and decibels, and they're like, oh, it's as loud as a jet taking off or whatever. Like, it's like, yeah, sure it is. Anyways, yeah, so there you go. Everybody cool? Another instance is the Richter scale. What do we use the Richter scale to measure?
No, intensity. Don't say anything to you. It's just like no, shut up.
Radiation.
No, it's not radiation. You're wrong. It's
I've heard it.
It's waves. It's waves. Something with waves. It's earthquakes. It measures earthquakes.
Earthquakes.
Let's
Yeah.
go.
Paul's pretty excited about that.
You're wrong. I'm sorry.
That's okay. So the Richter scale measures intensity of earthquakes or magnitude of earthquakes. So the R is what I'll call the magnitude of earthquakes. And I'm just abbreviating earthquakes with EQ. So when an earthquake happens, you have like normal ground, and then the ground kind of goes up and down. The total displacement in either up or down is what alpha is. That's, if we're talking about something that's moving up and down like that, though, it's really the same thing as a sine or cosine wave. So we'd call that the amplitude.
Like an aspect or a wave.
Yeah, sure. And typically the measurement, or the unit of measurement we make with that amplitude is micrometers. That's the Greek letter mu in front of the M for meters. I think, what is micro? 10 to the negative 12th? Ninth? Something like that. I'm not positive. Yeah. It's one of the major ones, because every 3 is like the one that you know.
Wait, that's nanometers.
Micro.
Okay.
Yeah, that U is the lowercase Greek letter for M. It's supposed to look like a fancy M or something.
Oh, so it's neither.
That's the mu symbol for micro. I believe. It's been a while since I've like explored the prefixes for that far down the SI table or whatever. T is the time it takes for the ground to go like base level, up, down, and back to base level. In the parlance of trigonometry, that would be the length of a period, right? Where we've gone up, down, and then back to the midline, right? And that period is measured in seconds. And then to talk about the B, where is an earthquake most intense? What is that location called?
Epicenter.
The epicenter.
You did not.
Yeah, I did.
And as you move further away from the epicenter, what's going to happen?
Less.
Less intense. So depending on where the tool you were using to measure your earthquake is, you need like some kind of correction factor that like says, okay, well, the earthquake was in San Francisco. My measurement tool was in Sacramento. So I have I didn't get the full rock in. So I need some kind of like correction factor that's going to account for how far I was away, right? So that's what this B is. So that's what the B is doing. All right. Let's look at an example. The infamous San Francisco earthquake. I think it's the title infamous because it was the most intense on record earthquake in the continental United States. I emphasize continental because I'm sure that there's something in rural Alaska that was probably worse since you're sitting on that ring of fire there, at least through parts of Alaska. Has a Richter scale magnitude of 7.5. How many times more severe was the most severe earthquake ever recorded? The 1960 Chilean earthquake that had a Richter scale magnitude of 9.5. So hopefully nobody's surprised when we want to use the Richter scale model to do this. Right? Nobody's shocked by that, I'm hoping, right? Right? All right. So when you read this, it doesn't seem like you have enough information to fill in the equation, right? Well, I notice that I have two Richter scale measurements. So I'm probably going to be forming a system of two equations. One for San Francisco and one for Chile. Everybody's cool with that. And when we talk about the severity, which one of these measurements do you think is a better measure of severity? It's going to be like how much up and down there was, right? So really the severity we're going to be looking at is like a ratio of these alphas. So I need an alpha for San Francisco. And I know I'm going to need a different alpha for Chile. So I'm going to use alpha 1 and alpha 2 there. Cool so far? All right. Now it seems like we still don't have a value for B or a value for T. So let's think about this for a moment, right? The measure or the Richter scale measurement for R1 at 7.5, that's a Richter scale measurement, right? And the 9.5 is a Richter scale measurement for Chile. So one of two things could happen. Either those were measured at the epicenter, so the B value is 0, or they were not, in which case the correction factor for B was already applied to it. So we can just kind of assume that the B values were either 0 or just identical. Does that kind of make sense? Since I'm looking at a Richter scale measurement already. So I can just assume that the B1 is equal to B2. I'm just going to call them both B since they're the same. Is that all right? The other piece is the period. And again, if I don't have that, I kind of need that to be able to do this. So again, we're given no indication of what the periods would have been in this. We're going to make the same assumption, just that the two periods were equal. Again, if you're talking about a period, how long it takes to move up and down, that's probably pretty constant for earthquakes of relatively similar intensity. Okay. So to solve this system, I'm going to subtract the San Francisco earthquake from the Chilean earthquake. I'm going to choose to do that order because I want the output of my difference of logs to be a positive number. It just makes everything arithmetically a little bit simpler. So 2 is going to equal log of alpha 2 over t plus b minus the quantity log of alpha 1 over t plus b. Actually, maybe we'll write this 9.5 minus 7.5 here at the step, just to make it super duper clear. All right, so I know that I can like distribute the x or the negative sign and do that. What do you notice can happen now? Yeah, the b's cancel out. Great. Then what can I do with those two logs?
Log them out.
It's not a computer.
Do you do like a sort of like the property?
Yeah, which property, in fact, would I use here if they're being subtracted? The quotient property. Very good.
What you could do is use product property, but you're adding the minus.
Yeah, you could do a power and then a product, sure. Since they're both fractions, I'm going to write this like with a division symbol in the middle rather than a fraction, because fraction on top of fraction is a little weird looking. But remind me again, go back in your time machine, go back to elementary school, how do we divide fractions?
Switch and multiply.
Yeah, so you make the reciprocal of the one on the right and multiply. I remember from way back in elementary school, my math teacher told me dividing fractions is easy as pie. Flip the right and multiply. And it must have worked because I still remember it 25 years later or whatever. No, longer than that. 30 years later or something. So I'm at this spot. Everybody cool? Okay. Next up, we gotta get rid of that log, right? How am I gonna cancel out a log?
Oh, you could do the what log means because it's log.
You turn it into an exponent, right?
That's what I mean. Yeah, exponent.
So you can use an exponent base to cancel logarithm. Great.
Would it be 10 to the power?
Yeah, and the exponent base you'd want to use in this case is 10. Why 10?
Because that was what math is.
The base of that logarithm is 10. We know that that's the common log when there's no subscript there. So what this is telling me then is that the Chilean earthquake was 100 times as severe as the San Francisco earthquake.
Yes, all you have to do is multiply the log by whatever it is.
not multiply. That's an exponent base. So you have 10 to the log of yada, yada, yada. Not 10 times.
Right.
Right. Is that okay, everybody? Okay. So another model is acidity. What do you measure acidity? How do you measure acidity? Or what unit do you use? pH. Great. So the formula for pH is negative log of the concentration of H plus. So pH measures the acidity of a substance. And how does the pH scale run? 10 is not the biggest.
0 to 14, right?
0 to 14, okay. So we have acids and we have bases, right? Which numbers correspond to acidic things?
0 to 6.
Well, I'll call 0 to 7, but okay. And then base goes,
8 to 14.
I'll go 7 to 14, where neutral is at exactly 7. So I'm going to do it like
So does
that.
it count as like 7? It goes to 7, but 7 goes to neutral.
Okay, would you prefer me to write it as like a set notation where we can have like,
Yeah.
there you go.
Oh, I guess it's fine.
And actually we should have a bracket here at 0 and a bracket there at 14, right?
You're including.
Yeah. Cool. Now everybody's happy. Very good. And then when we put a bracket around a substance in chemistry, what does that mean?
You can, Jackson was a fun guy.
This means the concentration of, in this case, hydrogen ions. Hi, Miss Anderson.
Just popping in for a treat.
Oh boy.
Would you
Let
like
me.
a Coke, a Coke Zero, a LaCroix?
I'll take a regular standard
And would you like some skinny pop or some popcorners? Chips?
Sure.
Cheddar, spicy?
Yeah.
You want a Tootsie Pop?
No, thank you.
How about for our girl later?
We're not at some point as far as our comfort level is.
I gotcha.
You know, it's
My
the first one.
My older one's 19, I still don't have Tootsie Pops. Thank you, Mr. Beard.
You're welcome. Thank you. Okay. And again, how do we measure concentration in chemistry class? You guys remember that?
Moles.
Nope. How about molarity,
Wow.
which was moles per liter,
Wow.
is the typical measurement for concentration. You could also use molality, right? That would be the other one. But nobody really uses molality, it seems like, so.
I'm in regular.
But you do the same stuff.
I had to learn this yet.
You have to learn moles.
I learned moles, not moles to a liter
That's
though.
All right. So let's look at an example. A really sour lemon is found to have a pH of 2.2, and a bottle of bleach is found to have a pH of 10.2. Part A says, what are the hydrogen ion concentrations of the two items? Okay. Well, hopefully nobody's surprised when we bust out the pH formula to do this, right? Super clear. What?
I'm a little surprised.
You are surprised. Well, you're just being a jerk right now, so that's okay. All right. I'm teasing. I mean, unless you wanted to be a jerk, in which case, mission accomplished. No, I was teasing. Not annoyed, just being a booger. All right. So what are we filling in for the pH part?
2.2.
Woo!
Let's do
Ooh, thank you. And then to solve for the concentration of the hydrogen ion, what's the first thing I should do? Yeah, get that negative out of there. So we'll divide by -1 or multiply by -1. They're both going to accomplish the same thing. I just got to get that log part by itself. And then how are we getting rid of the log?
Base 10.
Exponent base 10. Yep. So I have 10 to the -2 is equal to, -2.2 is equal to the concentration of hydrogen in the lemon. So I'll just go to my trusty old friend, the calculator. And I get about 0.00631. I'm going to write that in scientific notation. And I'm just writing this in scientific notation because I know where it's going later. Because are there going to be more hydrogen ions or less hydrogen ions in a basic thing?
Do you want us to, for our answers, to write it in scientific notation, or does it not?
I'm explaining to you why I'm doing it right now. So is there going to be more hydrogen ions or less hydrogen ions in a basic thing?
More. Acids have more.
Acids have more. So we should have less hydrogen ions in the basic thing, right?
Yeah.
So it's going to be even less. So I'm going to expect something with like a lot of zeros in front. So I'm already just going to jump right ahead to using scientific notation there because my calculator is probably going to give me an answer in scientific notation at that point anyways. So I'm just kind of getting a head start on that. And to solve this guy, we're going to be doing the exact same thing, right? All the algebraic steps would be exactly the same. So I'm not going to rewrite them. Everybody's cool with that idea?
Yeah.
Let's just go to the calc. Oh, man. Did you hear the joke about the pencil with the broken tip?
No.
Ah, never mind. There's no point. All right, so we got 6.3 times 10 to the negative 11th, or 6.31, I guess I should say. Cool so far? No big deal. Part B, it says how many times greater is the hydrogen concentration of the, probably should say lemon here, than that of the bleach. I think that's probably just a typo, since the bleach clearly would have less hydrogen ions than the lemons. All right, so for part B, if we ask how many times greater is something, what operation are we really talking about? How many times greater is one thing than the other? What are we really going to be doing there? Division. I don't know. So when I do that, I get 10 to the 8th. Oops. So it's that lemon has 100 million times more hydrogen ions than the bleach. It's a lot. It's almost like acidic things have a lot of hydrogen ion content, a lot of hydrogen ions floating around in them. Shocking. Chemists in the room. Okay, one more model to talk about here, and we'll call it quits for today.
Is there activity? Thermodynamics.
Cooling.
Cooling. You got it there, don't worry.
So Newton's law of cooling describes why your mouth gets burnt by your pizza rolls when you take them out of the oven. So it's basically describing how hot objects cool down. So this is the formula for Newton's law of cooling. T of T is the temperature of a substance. T minutes after removal from your heat source. So that would be like, 3 minutes after you pull your pizza ovens out or pizza rolls out of the oven, and you take a bite and your mouth is filled with like lava pizza filling and you burn your mouth. Right? Everybody's had that happen to them, I bet.
Pizza roll?
Yeah.
Yeah.
They're like notorious mouth burners.
Hot chocolate.
Oh, that's a good one.
TM is the temperature of the medium. So that would be like, in the case of our pizza roll example, that's the air surrounding the pizza rolls. If you're like a medieval blacksmith and you're pulling the sword out of the furnace and you beat on it a little bit and you stick it in the cold water, it'd be like the temperature of the cold water. That process, I think, is called annealing. Anyways. For all those medieval blacksmithing fans in the room.
Does that just make them metal stronger?
Yeah, it like makes the steel harder, so it's less likely to bend on you.
I gotta start taking notes to be a blacksmith.
Well,
I'm gonna make horseshoes. That'd be sweet.
That's a farrier, actually, is the technical term for that.
yeah, get it right.
I'm gonna be a farrier.
All right, T naught is the temperature of the substance when removed from the heat source. K is a constant, but that constant is specific to the substance that you're heating up. So like, if you cook a grilled cheese sandwich and you make some soup and you take your boiling soup and pour it into a bowl and you take your grilled cheese sandwich off the stove and you wait a minute, you can probably eat your grilled cheese sandwich, but the soup still burns the bejesus out of your mouth. Different rates of cooling because different substances have a different constant of cooling, right?
Is there a way to calculate that?
We'll talk about it. So the T is just the time that it's been out of the heat, right? So you take your pizza rolls out of the oven, you put them on top of the stove, you wait 5 minutes, your T is 5. All right, let's look at an example. A hard-boiled egg is heated to 96 degrees Celsius, then placed in a pot of water at 16 degrees to cool. After 4 minutes, the temperature of the egg is now 45 degrees Celsius. How long will it take to cool the egg to a temperature of 20 degrees Celsius? Hopefully by reading this, you're in no doubt that we're going to be using Newton's law of cooling here, since we're talking about cooling a boiled egg. if you read this, which of these parameters is not ever mentioned in the question? The constant, K. So what we're going to do is we're going to have to be finding the value for K first before we can actually answer the meat of the question here. So it turns out that these first two sentences are going to be, we're going to use to find the value of K. And then once we have that K, we can actually answer the meat of the question. So Paul, if you wanted to conduct an experiment to figure out what the K is for a substance, you just have to basically repeat what we're doing here. So you heat it up, you measure how hot it is, you let it cool down for a little while, you measure the temperature it cools to, and then should be able to use that information to solve for your K. So that's what we're going to do here. The 96, where is that going to go? That is the initial temperature, yes. When we pull that out of its heat source, absolutely. Where's the 16 going to go? Yep, the temperature of the surroundings. So that's the TM. The M stands for medium. It's like the medium of heat transfer, I think is the technical term there that they're using. Okay. 4 minutes is definitely the T. And then, so the 45 has to be our T of T. Everybody cool with how we set this up so far? All right, let's solve for K. What do you want to do first? Excellent. Subtract 16. And then 96 minus 16 is 80. So I'm just going to go ahead and write that in the more convenient form. Next, what do I do? Divide by 80. Yeah, we got to get that exponential piece by itself. So let's get that 80 out of there. Now we want to cancel that exponent base of e. We're going to need to use a logarithm. The logarithm we want to use is log base e, also known as the natural log. And my last step would be then to divide by -4. I'm going to write it as multiplying by the reciprocal, just because I don't want to confuse myself later if I go back and look at that, whether that -4 is inside the log or outside the log. If I write it like that, it's super clear to me that it's outside. So now it's calculator time. God bless you. So I get positive 0.254-ish. So again, what we did here was just kind of answering the yellow part of the question. The meat of the question here is green. It says find how long. So what are we going to be solving for? In a how long question? Time! Not that hard. Now, it says how long will it take to cool the egg to 20 degrees? So the initial temperature, is that any different? No, still 96. The temperature of the medium, is that any different? No, still 16. So where's the 20 got to go into? Goes in for T of T. And my K now is 0.254. And this problem looks remarkably similar to the previous one, right? Okay, first step. Subtract 16. Very good. Next step. Divide by 80. I would point out here, I realized that I could reduce that, but I'm just going to type into my calculator anyway, so I'm not even going to hassle with any of the reducing that I could do there. Natural log it. You got it. And then my last step would be
Divide by negative, or multiply by the reciprocal 1 over negative.
you can certainly say divide. It's totally okay. I'm just explaining to you why I'm writing it as multiplying by a reciprocal. And it's just for clarity's sake. So I have 1 over negative, and I'm going to use the ants command so I can just take the entire decimal there just to make things a little bit more accurate. So I get about 11.81 minutes. Any questions so far, dudes and dudettes? My studentos? Best friends? Nothing? Feel good? This is where I wanted to stop. Usually we had a lot of questions in the other classes, so there was, we chewed up 20 or 30 minutes at the start doing questions. You guys didn't ask any, so that's fine. That's why we're done more earlier than usual. But you guys could now do 131 through 138. What do we got here? 30 minutes or so left of class. Why don't you guys try to burn through some of the problem set stuff while we got a chunk of time here? You know what I mean? It's that much less time you have to waste this weekend when you probably want to be studying for your AP test next week. Or this week.
And 1 Monday.
Oh, well, Paul, you're still in a lot of trouble.
Yeah, on Monday, Paul.
So,
That's a real concern.